All right. Hello, it's Friday. I can tell it's Friday because the class is thin. The numbers are thin today. You guys should come to class. I get lonely if you guys aren't here. I know, exactly. I'm talking to the wrong group of people. But some of you guys just might be like right on the edge of thinking, I don't need to come to class anymore, right? And the problem is like this is right around the time in the semester where I've started to actually learn people's names, and so I will see who is here. Anyway, it's Friday, I guess. I don't know, maybe this is like the excitement's worn off. This is like it only took 3 weeks. I'm a little disappointed. All right, so today we're going to talk about threads. We're going to keep going with our sort of unit on the processor. We've talked about some problems with the processor that the operating system is trying to address. We've discussed the mechanisms that the processor provides the operating system to help manage it. And now we're going to sort of introduce the main abstraction that the kernel uses to think about how to multiplex the CPU. So we'll talk about threads. We'll discuss 2 different ways of implementing threads that you guys will sort of probably come across and the consequences of those, and a little bit about thread states. Next week, we will finally get to synchronization sort of full on, which will be good timing because as of today, you guys have 4 weeks left before everything up through assignment 2 is due. I have this bad feeling that people in this class are grossly underestimating the amount of work that assignment 2 is in particular. How many people have started assignment 1? Okay, that's good. Okay, so you guys are just getting how many people have started assignment 2? Okay, good. No, not good. It would be better if there were more hands up. But so yeah, I mean, assignment 2 like assignment 2 and assignment 3 are really a lot of work. I mean, they're like assignment 2 might be like 8 times the work of assignment 0. Maybe like 4 or 5 times the work of assignment 1. So if you guys are sort of moving slowly moving slowly in the earlier stages of some of these assignments, please come and get some help, and also just start working on them, right? Like spend a couple hours a day just hacking on these assignments. That'll get you guys going, all right? So there's occurred this issue with the exam date, which is that it's during the career fair. Part of me doesn't care about that because there's career fair before and after, but I understand that the career fair is like somewhere far away, and you guys will. Is that true? Where's the career fair? Is that far away from here? Yeah. Okay, yeah. So maybe you might lose like 2 hours of the valuable time that you're going to spend in line waiting to talk to the Microsoft recruiter. But I'm considering maybe. So the problem is I don't want to do the exam on Friday because how many people won't be here the Friday before spring break? Yeah, see, I anticipate this. And some people actually even have a good reason for it, which is worse. So I don't want to do it Friday, and then maybe, so just a quick show of hands. I think we'll do this on the Piazza site quickly. How many people would prefer to have the exam before spring break? How many people would not be angry with me if we had the exam after spring break? Okay, well that might be okay then, because I'm just not sure we're going to have covered enough. I think the shift in the dates in this semester, which seems to have caught everybody by surprise, by the way. I got this great email the other day that said that someone finally realized a month and a half into the semester that there are exams scheduled during commencement, like during the commencement ceremonies. I was like, whoops, I'm glad the people who do commencement talk to the people who schedule exams like at least once or twice a semester so that we can work these things out. So anyway, I think because of the shift in the dates in the semester, it feels to me like spring break is earlier than it has been in the past. So maybe we'll do the exam afterwards so that we can just get through enough material that we can cover about half the stuff. So we'll do this on the website. All right, I just thought this would be fun. I don't know how many of you guys know this. Debatably, and there's something recently that happened that made me think of this. Debatably, who do you think is the most famous alumni of this class? The most famous? No, definitely not me. Well, thank you. That's so sweet. No. I pale in comparison. What's that? No, don't look there. You guys are cheating. Yeah, this guy, right? And it turns out, how many people noticed that Facebook turned 10 recently? So 10 years ago, Mark Zuckerberg was taking this class, right? And in his spare time, how many people have seen The Social Network? Do you remember there's that one scene where the brothers that sued him are like, he's telling us he's spending all this time on this operating systems class or something, you know? And they think it's just BS, right? Well, it turned out it was at least partially true, which is funny. I don't think people watch the movie realize that. So yeah, he started this in his free time while taking this class. His project partner was not necessarily super happy about the amount of effort he was putting into the Facebook as opposed into the kernel. But it turned out it had a happy ending. His project partner, Andrew, went to work at Facebook and now has a big chunk of Facebook equity, which is probably worth a massive amount of money, right? So anyway, sometimes it pays to be patient with your project partner if the side project they're working on is eventually going to be worth billions of dollars, right? Obviously, it's hard to know that like in the moment. So anyway, this is kind of fun. I knew Mark a little bit when he was taking this class. He wasn't someone I interacted with a lot, but all right. So let's talk a little bit about wait, how did this get here? Oh wait, that is review. Okay, so let's do a little bit of review of the material from last time, right? Last time we talked about how we actually sort of move things on and off the processor, and we referred to a transition between two threads as a context switch, right? And then all of these abstractions that we're building up, what are some of the problems with the CPU? I'm going to have to stand over here to shield it from you guys. You can't see the answers. Whoa, slow down. Okay. So what are some of the problems that you didn't just see on the slides that the operating system is trying to correct about the processor? Yeah.
You can only do one thing at once.
One processor can only be executing one thread of stream of instructions or thread at a time, right? You might only have one or at least a smaller number. And what's the other problem? Yeah.
CPU is very fast.
Yeah, so the CPU is much, much, much faster than other parts of the system, right? And so what we want to do is we want to make sure that, you can think about it this way. A good operating system will make your device feel as fast as the processor. A bad operating system will make your device feel as slow as the disk, right? So I don't want my entire system or all my applications to be bottlenecked by the slowest parts of the machine. I want to sort of make sure that I can keep the fastest parts busy despite the fact that the slowest parts are also involved in most of the things that you guys actually do, right? All right, we talked a little bit about the historical evolution of computing and how, as computers, mainly as computers became sort of ubiquitous and very inexpensive, the sort of relationship between humans and computers changed, right? So what was batch scheduling? This is a form of sort of job management that was used on very early systems. Somebody from this side of the room. Yeah.
Like a queue.
Yeah, so a batch is sort of like, it's a queue. I run one job at a time, and the job has access to the entire machine, and when the job completes, then I run something else. How many people have ever used this kind of system? Yeah, so these systems actually have survived until today. Or something akin to this, right? Some of you guys may have used Amazon Web Services, for example, and other cloud computing platforms have these type of queue-based processing systems, and they're usually for tasks that don't have a lot of timeliness requirements, right? So just have a bunch of work, jam it all into a queue somewhere, and then I have maybe one, or now maybe many, many different machines that are pulling stuff out of that queue and executing it. So that's kind of a variant of this, right? The early batch scheduling systems there was sort of a one-to-one mapping between the task that was executed and the number of machines, which isn't necessarily preserved today. But this concept is still with us, with this idea of just sort of batch scheduling, right? What's the problem with batch scheduling? Yeah. Right, so if I go to this old model of batch scheduling where the job had full access to the system, any slower part of the system will leave the CPU idle, right? So anything that task does where it needs to wait, because there's only one thing running, there's nothing else I can do while that task is waiting, right? So slow devices can idle the CPU, right? All right, so remember, we talked a lot about this illusion of concurrency that the operating system is trying to create, that sort of harnesses your perceptual limitations, or I should say exploits your perceptual limitations to make the system look like it's actually doing many things at once, right? How do we do this? On a uniprocessor system, there's only one thing that's running. Yeah?
Every time a process makes a switch call, it will kind of put that over to the side of working on the process.
Yeah, maybe, right? I mean, the general idea here is I'm rapidly stopping one thing and running another, right? So it's not that two things are running simultaneously. It's that they're time sliced so in such a fine-grained way that you can't tell the difference, right? It's like the difference between sort of still images and motion pictures, right? That once I get them fast enough, it looks to you like they're running simultaneously, despite the fact that they're actually not, right? Clearly, they can't be on a uniprocessor system. There's only one processor, right? All right, so we pointed out some ways that the operating system gets control, right? One is when a hardware device needs some attention. Another one is where a process makes a system call. But how does the operating system make sure that it regains control enough to provide this illusion of concurrency? How does it make sure that there's not some special case where, because the software doesn't need help and hardware doesn't need help, this one piece of software could run for a potentially long time? James? Yeah, so I create a special source of hardware interrupts that guarantees that only a specific amount of time is going to pass before I get a chance to run, right? And the consequence for you as a programmer is something we'll start talking about at the very end of today's lecture and continue talking about next week, right? But essentially it means when you start doing multi-threaded programming, your thread can be stopped when? At any moment, right? Again, there's no lineup on a fully preemptive system between what you're doing as a thread and when you can be stopped, right? You can be in the middle of what looks like a single instruction, right? A single line of C code can block in the middle and leave you in some sort of weird state. You can be pushed to the side. Somebody else has a chance to run. When we restart the thread, what is the operating system's goal? Yeah, I want it to look like nothing has happened, right? The problem, of course, is that when we start talking today about multi-threading, there are other threads that might have run, and so stuff may have changed, right? And the entire sort of goal of next week's set of lectures is to talk about ways that we make sure that multiple threads can collaborate safely, despite the fact that they are going to be modifying shared resources, right? It's a topic called synchronization. All right. What is the state of a thread? So when I actually stop a thread and put it to the side, what information do I have to save to make sure that I can start it up in the exactly same spot next time it runs? Yeah? Yeah, so it's essentially registers, which includes the program counter normally. And then also I have a stack, right? Every thread has a special area of memory where it stores local variables in other state. Now when we start talking about multi-threading today, it turns out that this stack is not necessarily entirely private, right? You can actually have sharing between multiple threads across their stacks, assuming they're in the same processor within the kernel, right? Some operating system vendors have used this fact to do these very clever synchronization approaches that don't require any additional memory. They just use the stack of the threads. In general, accessing information on another thread stack is a very bad idea, right? Because that thread could change that information at any time, and you're going to be in trouble, right? All right, context switches are free, easy, something I could do at any moment. No, they're not free, right? They require executing a fair number of instructions and saving potentially a lot of state, right? And so context switching creates this cost. So going back to the timer interrupt, and this is something that we talked about on Wednesday, but something you guys can sort of reason through, right? What's the trade-off with the rate at which the timer can fire, right? So these timer interrupts sound awesome, right? From the kernel's perspective, it's like, okay, because I'm the kernel, and who knows what's going to happen when I'm not in charge. So I'm going to make the interval between these interrupts really, really, really tiny, right? So that I have a lot of chances to make sure, like, as soon as you hit that key, I'm going to run, and within like a microsecond or a nanosecond, and I'm going to make sure that that key is drawn immediately, right? What's the problem with this? Yeah, Damien. Yeah, so when we start talking about scheduling, right, we're going to start to look at the overhead of scheduling, right, and the overhead of doing these context switches. Now, as a user of the system, right, do you appreciate the time that the kernel spends saving the state of threads and choosing which thread to run? Do you appreciate that as a user? No, that's just dead time, right? That's just time that the machine isn't doing what you want it to do, which is to run your applications and do cool stuff, right? So as I make the timer interrupt shorter and shorter and shorter, the amount of time, the overhead of doing these things starts to dominate the amount of time that the machine is running, right? What happens if I go in the other direction? Let's say I make the timer interrupt really long, like a second. Then what's my problem? Yeah. Yeah, then I run up against these perceptual limitations, right? Then I could have an app that didn't paint for a second because something else was running, and that would start to look pretty bad to you as a user, right? You're used to this illusion of concurrency. All of you guys, grew up using these windowing systems in particular, which expose that quite directly, right? All right, any questions about this before we talk about threads today? All right, so we've been talking about threads, right? We've been using this term. I think you guys have some concept of what it means as a programmer. But what is a thread? From the perspective of the operating system, a thread has to mean something specific. So what is a thread? What does it consist of? Yeah. A thread is an abstraction, right, that we use to represent the CPU. Really a sub-process, because a sub-process is a process. But what is a thread supposed to reflect? Yeah. Yeah, so we think of threads as executing a series of instructions, but if you think about this, think about inside the kernel, right? The information that a kernel would store about a thread, or how a kernel would represent a thread. Yeah.
It might have a stack and its own block of memory.
So it has a stack, right? Again, we talked about threads having a stack. That's a place that, and the reason I need to know where the threads, why do I need to know where the thread stack is? Who cares? That's memory, right? That's not part of the CPU. What's that? Yeah, because there's this register called the stack pointer, right? And if I was trying, let's say I said, okay, I'm just going to let the memory management stuff, which we haven't talked about, I'll just let it deal with the stack. But the problem is, when I start the process up running again, I need to know where its stack is, because there's a register that it uses to know where its stack is, right? So it's also a stack, and then what else? Has its own program. We're getting closer. We can do these one by one. Registers, right? It's just a stack and registers, right? And really, it's just the registers, right? This is like a snapshot of the CPU at a given moment in time, right? And if you think about a series of instructions, right, it's just how that snapshot evolves over time, right? But from the perspective of the kernel, a thread consists of the state necessary to recover a particular thread of execution on a CPU, right? So it's really the registers and stack, right? So now, to distinguish between threads and processes, let's go through some of the components of a thread and a process and talk about how they're shared, right? So are registers shared between multiple threads? No. There's no way for a thread to access a register that's in use by another thread. I guess conceptually there could be on a multi-core system, right? But I don't know of any system that does this, right? And I think that would be odd and difficult to support, right? So registers are considered to be private. What about the stack? Shared between threads. What about between threads in the same process?
Yeah.
It can be, but is it usually? No, thread stacks are usually considered to be private, right? And if you want to share information that's stored on thread stacks, you have to do a lot of extra work, right? But between processes, thread stacks are stored in memory, and we haven't got this far yet, but the process memory protection that kernels implement will keep threads in multiple processes from accessing each other's memory directly, right, without additional mechanisms, right? What about the rest of memory? Shared, right? And this, in particular, when we get to synchronization, this is the root of your problem, right? If everything was private between multiple threads, you'd be in great shape, right? But a lot of the data structures and state that threads manipulate are stored in memory. And so if you're implementing a multi-threaded process, you clearly have this problem. But what's a potentially extremely complicated and extremely important multi-threaded process? What's that? Business contact information? Business transactions. Oh, okay, that's at least a little bit better. So that could be one, but I'm thinking of something a little bit more close to home. The operating system kernel, right? Big, complex, multi-threaded application where there is a lot of shared state between threads, and you guys will have to do a lot of careful synchronization for assignment 2 and assignment 3 in particular, right? What about the file descriptor table? Private to each thread, shared between threads in the same process? Shared between threads in the same process, right? Not necessarily between, processes. We went over this when we talked about processes. All right. So why do we use threads in the first place? Like someone came up to me after last class and was asking, this is a particular type of programming model, but why have you guys been taught? I mean, how many people have been taught to use threads to represent different things that are going on in a program? How else do you do it? How many people have written multi-threaded programs? Okay, well, you've done that for some reason, right? Why do we program with threads? Multiple threads, yeah.
They provide the illusion of concurrency, and they're also better than forming a holding process. The rest case and some file table and
Okay, right. So when we talked about processes, about the fact that the IPC mechanisms between processes are limited by the fact that the kernel is trying to protect processes from interference from each other, right? So that makes the communication between processes more difficult than communication within processes. So if I use multiple threads, it might be a way of reducing the overhead of trying to write something using multiple processes, but what else? What's another reason? Yeah. What? Okay, yeah. So in certain cases, right, if I had one thread, right, and it was trying to run the entire program, and it went off to do some network I/O, and it blocked, it had to wait for the network to complete some sort of operation, then there's nobody painting the display, right? And so the display is going to sit there and hang. So that's potentially a good reason, but there's something more fundamental here, right? Why? You can actually implement applications that work that way without using threads. Yeah?
Just the abstraction of doing more than one thing at once.
Yeah, I mean, it's a way to exploit the illusion of concurrency, right? The operating system has provided us with the ability to rapidly switch between threads, and now because I can allow the system to look like it's doing multiple things at a time, it's a good mental model for how programs work, right? When you write something like Firefox, for example, you have multiple tabs open, you want it to look like each one of those tabs is a completely separate thing, right? Like they're all alive, they're all loading multiple copies of the same web page or whatever, right? So threads are a good mental model for how we think about our applications, right? And the application's doing multiple things simultaneously, right? Now, how many people have ever done any sort of event-based programming? Yeah, okay, good, a few hands. So threads are not the only way to exploit this illusion of concurrency, right? And there are other techniques for doing this, and those techniques have been explored by people and used in certain cases when they can sometimes be a lot more efficient than threads. But threads, as a starting point, again, are a nice mental model for this idea of, there's one thread that's following the mouse around and redrawing the mouse on the screen, right? That's one thing that's happening, right? There's another thread that's in charge of figuring out what to do when you click on a menu, right? There's another thread that's, contacting the website that you just tried to load and downloading the content. There's another thread that's painting stuff to the page, right? So another reason to use threads is that threads can be a good way of encapsulating data, right? So again, we go back to the Firefox example. Each tab is sort of, distinct, right? It has its own, location bar. It has its own data it's using to render the page. So threads, in certain ways, sort of reflect the way the data within a program is already divided, right? And this goes back to the illusion of concurrency as well, right? I mean, threads allow me to hide delays, right? So somebody pointed out with a GUI type application, if I only have one thread, and that thread does anything that causes it to block or requires it to wait, the entire application just looks really unresponsive, right? So rather than having a thread that does everything, if I have one thread that's in charge of painting and I make sure that thread never blocks, then I can do other slow things in the background. Right? Again, this is not the only way to accomplish this, but this is a model that you guys are sort of used to, right? Because it's something that we've taught you since you guys started to learn how to develop complex applications, this idea of using multi-threading. So this is an example I like, right? So for people who haven't thought carefully about this, this is not a perfect analogy, but it's also like, in the space of analogies, a pretty good analogy, right? And I can't claim to have come up with this myself. This was Wikipedia, teaching me something. So So multiple threads within a single process are kind of like, if you've ever been to a restaurant where there's a bunch of people in the kitchen, right, all working together to prepare dishes for a meal, right? And what happens, of course, is there is not, now if you go to a really, really fancy restaurant, there might be an entire cook in the kitchen who is devoted to you, right? And is only cooking your food from start to finish, right? That's probably unlikely if you go to most restaurants, right? And so what's happening is the cooks that are assigned to cook for you are figuring out how to divide up these tasks, right? So, and a lot of times each one of them is sort of compartmentalized to work on one particular part of the process, right? So there's somebody who's doing one stage of cooking, someone who's using one piece of equipment, right? And doing everything that needs to be done with that piece of equipment as part of the process of creating a meal, right? And again, they're probably doing different things, right? They're not all, trying to use the same piece of equipment. They're not all doing, all of the cooking required to do each dish in the meal, right? They're sort of handing things off between each other and using themselves to sort of parallelize access to different parts of the kitchen. Also, because probably they're good at different things, right? That's one of the places where the analogy falls down, right? They're all, so here's some shared state, right? They all are working with the same set of instructions and recipes, right? And this can be kind of like a shared code base that multiple threads within a single process are using, right? Every thread within a single process has access to the same source code, right? They're all working off the same set of instructions, but they may all be in different parts of the recipe, right? They may all be doing different things, different blocks of code, right? One is here, one is there, but they're all sort of working with the same base set of instructions. They all have private state. What's the private state that each one of them has? What's your private state? Whatever's up here in your mind, whatever you're thinking about me right now, right? Like, this is a really stupid example, right? Like, that's an example of private state, right? But they can communicate easily. How? Someone could say, this is a really stupid example, right? I'm glad no one has said that yet. Yeah, so they all have their own private state, but the communication is quite easy, right? And they have to work together, right? They have to coordinate with each other in order to get things done, right? In order to gain access to resources, in order to make sure that things get done in the right order, right? So this is really, really critical, right? And how that communication is done, in some ways, shares some similarities with what we'll talk about when we start talking about synchronization, right? So let's talk about some naturally sort of multi-threaded applications. We talked about a web server a lot, right? Where frequently a single thread is used to handle each incoming connection, right? And again, sort of separate state, right? What is this particular connection requesting, right? Shared code base. They all are running the web server, right? They all have access to the same pages even, in terms of the content, but they're all doing different things. Each one of them is at a different state of sort of gathering the information necessary to serve the request and returning the result to the client, right? Web browser is my favorite example, separate threads for each tab. A lot of times we use a lot of multi-threading and multi-programming when we do scientific applications. Why is that? Does anybody know? Why are a lot of scientific data sets sort of relatively easy to apply multi-threading techniques to? Yeah. Yeah, so we call these sort of embarrassingly parallelizable, which has always struck me as a weird word. There's a lot of L's in it. Parallelizable data sets, right? So there are data sets where it's extremely easy to sort of tear them into small pieces and allow those pieces to be performed at the same time. And a lot of times, maybe this isn't even a perfect application for this, because a lot of times the reason we do this is because there's so little communication between these tasks that they can not only be run in multiple threads, but they can frequently be run in multiple processes or on multiple machines, right? All right, so going back to this question of why would I use multiple threads in the same process? Why wouldn't I just use multiple processes, right? Processes are so much more process-like, right? So much more powerful, yeah. Well, I don't know. I'll only have to do it a few times, right? But yeah, forecast some cost to it, at least initially, yeah. Oh, okay. Yeah.
Programmers get the ability to program threads.
Okay, I like where that answer is going, but it's not there yet. The programmer has the ability to program threads. Yeah. Well, I have to context switch between threads, right? And it turns out that in certain cases, it's actually, there might be a little bit more overhead in context switching between threads and different processes, but that's sort of like advanced ninja type stuff, right? Yeah. What's that? Right, but what I'm asking is why not, if I gave you a choice between, I asked you to do a particular task that required multiple computational units, and I said, okay, there's one way to do it with threads and another way to do it with processes. What's the downside of using processes? Damien?
I only have the idea of with processes, if you make another one, that's going to be exactly the same as the original.
Well, yeah, but then I just run exec and I have something new, right? But yeah.
It's easy to communicate using shared variables.
Yeah, I mean, the main reason here, right, is that IPC is hard, right? Communication between processes is hard because kernels are built to protect processes from each other. Inside the same process, do whatever you want, right? So you start firing off threads within your own process, and they've all got this big heap of memory that they all have access to, and they can do anything they want in there, right? And the operating system is like, hey, I don't care, you know? Like, you mess up, you crash yourself, right? You don't hurt anybody else, right? And sometimes the state associated with processes doesn't scale well as well, right? Each process has its own big chunk of memory and file tables and other things, right? So it turns out that despite the fact we talk about threads now in an operating system course, threads can actually be implemented in user space entirely by unprivileged libraries. How many people have ever used a user space threading library? How many people have used pthreads? Okay, well then you've used a user space threading library, right? So we'll talk a little bit about two different models, and this is something that we might come back to later when we look at design trade-offs and how we built these things, right? So in the user space threading model, this is sometimes called what's the M-to-1 threading model, right? What this means is that, and what this reflects is the fact that if you use a user space threading library, the threads that you use are actually not visible to the kernel. The kernel thinks that your process only has one thread. But internally, your process has lots of threads, right? And so M here is the number of threads that your process actually has that have been created by the threading library. And 1 is the number of threads that the kernel thinks that your process has. Yeah? Hardware-based, yeah. Yeah. Hyperthreading is one of those. I would have to even look up what's exactly meant by that term.
Look it up. I think it's like when there's two logical cores. There's one core you have two logical cores.
Right.
Around two threads. Around two threads.
Yeah, so I think that what that reflects is to the operating system, it looks like there are two cores, right? So I can actually schedule multiple threads on there, but there's some set of shared resources that the CPU is using, you know, like some shared registers, and the CPU is being careful to make it look like those are actually two logically separate threads. It's a great question, though. So why would a CPU do this? So we talked a little bit about the difference in speed in different parts of the system and the responsibility of different parts of the system to sort of, or different hardware versus software, essentially hardware versus the operating system, to eliminate those speed differences. Or mask those speed differences. So what do you think hyperthreading is a response to, right? It's something that's invisible to the operating system, right? The operating system just thinks, I've got two cores. And the hardware's like, actually, I only have enough registers for one core, but we're cool. You know, you give me two threads to run and I'll figure out how to do it. Why is hardware doing this, right? What is hardware exploiting here? The CPU is faster than every part of the system, but what part of the system is the hardware helping mask the delay of in this particular case? What's that? What? Well, yeah, I mean, other parts of the system are slower, but what specific part of the system? Yeah, it's actually memory, right? Caches or memory. So my guess is the way this is implemented is by when instructions stall or go to memory, that gives the processor time to do other things, right? Those latencies are not exposed to, this is sort of like out of order execution, right? Those latencies are not exposed to the operating system. but it's a question of hardware actually trying to hide the relatively small latencies to go to memory, right? So here's a, this is a good sort of line of digression, right? Why? So I have a proposal for a clever new processor design, right? So we'll call it the Guassessor. What it's going to do? It says, okay, it's never going to see the light of day, so no one will have to complain about the stupid name. What the Guassessor does is when there's a memory stall, right? So when an instruction that you're executing actually has to go to memory, it interrupts the operating system so the operating system can run another thread. That sounds pretty awesome, right? Why not do that? This is essentially what I do with hardware, right? I mean, when a process uses something like the disk, when a thread makes a disk request, we'll get to this later in the class, I put it to sleep and I wake it up when the request completes. So this way, when the thread needs to access some memory, because memory is slow, right? I'll just put it to sleep and then wake it up in the memory. Yeah.
Well, you run into hardware concurrency issues if another thing tries to read memory?
No, it's not even that. I mean, that's a potential problem, but.
Means your operating system have to access memory as well? So wouldn't you come back to the same problem where you have to go access memory?
Well, let's put it. How about this? When I'm in privileged mode, I don't worry about that.
Okay.
Right? Yeah.
Becomes too expensive?
Yeah. I mean, look, memory is slow, right? But entering the kernel is slower, right? So if I've got to wait 20 cycles or 200 cycles for some sort of memory operation to complete, you remember that set of instructions we started to look at for entering the kernel? That's long, right? So this is why this is a bad idea, right? The kernel is too slow to hide latencies in memory access. It's fast enough to hide latencies with the network and with disks and with other really, really slow devices, but memory is too fast, right? It's slow enough that we might want to hide the latencies, but it's too fast to involve the operating system, meaning that CPUs and hardware do this themselves, right? That's the source of all these really cool games that CPUs play, right? Is to hide memory latencies, right? And the reason the operating system doesn't get involved is it's too slow. Okay. So back to the threading models. I have the M-to-1 threading model. The operating system has no idea that there's multi-threading going on. It's entirely implemented by user space libraries, right? And we'll show you a little piece of how this works in a second, right? Little bits of C that you never knew and hopefully will never use again after you see them today, because this is stuff that will make your code completely 100% unreadable. So unless you're entering some sort of obfuscated code competition, don't use these snippets, right? And the other threading model is that threads can actually be exposed by the kernel, right? I can't remember what version of Linux it was, but for a long time, Linux did not support multiple threads running within the same process. And so if you wanted multi-threading support on Linux, you used a threading library, right? At some point, Linux started to do this. Now you have these system calls that you can use to create new threads. But that was, relatively, I don't know, it's probably still a decade ago, right? For me, it was a recent, a recent, my life is going very fast now, so this was a recent development. This we call the one-to-one threading model, right? Every thread within a process is visible to the kernel, and threads are created by making a kernel system call or involving the kernel directly, right? Yeah?
In the M-to-1 threading model, how does the context switching happen between the threads?
There we go. Okay, so let's get here, right? How is this possible? How do I do a context switch? I just told you all this stuff about how operating systems do context switches, right? It turns out that because switching between multiple threads in the same process doesn't involve any sort of multiplexing that the kernel necessarily needs to know about, there's no kernel privilege that's actually required, right? Think about it. All I have to do is write down all the registers I was using, save that state somewhere else, and then load another set of registers and let some other thread run, right? There's actually nowhere in there where kernel privilege is required. So how do I save and restore context, right? So the C library has this fantastic set of functions called set jump and long jump. Has anyone used these before? Oh my gosh. Oh really? Were you entering an obfuscated code competition or?
So it was I think it was class in school assembly.
Oh, okay. Yeah, maybe you might have looked at these if you were doing really low level programming, right? So let me get to set jump. I just want to show you this example because it's fun, right? So what set jump does, oh, sorry. There is something here. So what set jump will do is set jump will essentially, this is what's called the jump buffer. This stores the state, right? And what set jump will do is actually store the state of the thread at this point, right? And what long jump will do is long jump will actually restore that state, right? So this is sort of like the process of saving context, and this is the process of restoring context, right? So how does this, what will this following code do, right? So this is pretty awesome. So it starts going through the loop, right? And I'm printing off the value of I, and I get through 5, right? And now I do some fun stuff, right? So I'm trying to remember. I think this returns 0 the first time. Yeah, there we go. This returns 0 the first time it executes, right? So if such jump saved is equal to 0, then I'm at this port. So I've set my state, right? And now I print saved CPU state, and I break out of the loop, right? So you would think that if I just kept going here, this loop would have ended it would have ended at 5, right? But actually, the way the flow works, I break out. I now restored is this flag I'm just using to figure out what to do here, right? Otherwise, this would be, I think, an infinite loop. So if I haven't restored my state yet, I call long jump, right? And what long jump does is it warps me right back to here. The only difference is this time the call returns 1. And now I'm in this bottom part of the loop, and I keep going, right? So what will happen is I'll come through here, 5, I jump out of the loop, and then I jump right back into the loop and finish the loop and keep going, right? Again, this is not a way to write readable C code, okay? Because it violates all of the assumptions we make about code flow, right? Yeah? What's that?
I think it was like math, but it wasn't the.
Yeah, there probably are other libraries that do similar things, right? But again, the whole point of this example is just to show you that this is possible, right? This is done using the same mechanism that we use to do a context switch, right? What long jump does is it restores all the registers and the program counter that were present when this call was made, meaning that here I am again, right? In exactly the same spot. And I'm assuming that what set jump and long jump do is they probably borrow a register to store the return count, right? So that's how set jump can return 0 once and 1 the second time, right? So this is pretty wild, right? Kind of weird. Let me go back to this, right? So I can use this, I can do this in C, right? Now here's a question, right? So here's something that does require kernel privilege, right? Saving and restoring state, it turns out, doesn't require kernel privilege, but what does require kernel privilege? How does the kernel preempt threads? What's that? The timer, right? And the timer does what? It generates an interrupt. What happens when the interrupt fires? Yeah, but one of the things on that list is I raise the privilege level, and I enter the kernel, right? I start running the exception handlers that the kernel has loaded there. So in order to handle the hardware timer interrupts, I have to be the kernel, right? That's really important. So if I wanted to implement threads in a user library, how do I preempt other threads? I can't stop a thread from running using the timer. Because when the timer fires, the kernel will run. And then, because the kernel has the kernel has no idea that I'm doing any multi-threading, right? So it'll just run some other process maybe, or whatever, right? But it's certainly not going to help me switch between threads. Any ideas? What's that? Ah, there we go. Signals, right? Woohoo, we found another use for signals. Right, essentially what happens is that the user processes can ask for alarms to be set to them periodically, right? An alarm is a signal sent by the operating system. It causes a particular piece of code to run in the user process. And that code can be, if you're using a threading library, some sort of thread scheduler that may stop the current thread, save the state, and start up some other thread, right? What's one big difference in terms of sort of protection here, right? Can a threading library, can threading libraries protect multiple user threads from each other? If I'm a malicious user thread, and I want to run forever, I'm sick of this pthread stuff, I'm out of here, right? I'm the most important thread. What could I do? Hey, just disable the signal handler. Like stop, have the operating system not send the signal anymore, overwrite the code that's handling the signal. I mean, there's all sorts of things I could do, right? Remember, this is inherently cooperative, right? The kernel is dealing with threads that are in multiple processes. It has to have a way to get control. If you're going to run multiple threads in your own process, you better make sure those threads are friendly, right? And don't try to interfere with each other, because they can, right? So there's no way to really enforce this. So if we just think about these two threading implementations, it turns out, despite the fact that some operating systems have sort of advanced potentially by allowing you to create threads that are visible to the kernel, both of these approaches have advantages, right? So for user space threading, what is one potential advantage with respect to kernel threading? I'll call on new people. Yeah.
Easier communication between the threads.
What's that?
Easier communication between the threads.
Well, remember, when I do kernel threads, those threads are still running in the same address space, right? They're still running in the same process, and so the communication mechanisms are the same, right? So there's no real difference in that. Yeah?
You don't have as costly context switching?
Yeah, right. So the cost of entering the kernel could potentially be avoided, right? So I may not have to save all the state that the kernel has to save, run the kernel scheduler, which might be quite heavyweight. I can do things in user space without actually crossing the kernel boundary, right? And it turns out the thread state that's stored by using threading libraries can actually be a little bit smaller, right? Sorry this all came up at once. One con, right, of this approach is, remember, and this is one of the reasons why operating systems have started to add this as a feature. To the operating system, there is only one thread. And so a user space library that's using multi-threading will never have access to multiple cores at the same time, right? You might have 16 cores on your machine, but if you're using pthreads and the operating system thinks you only have one thread, you will only be scheduled on one core, right? If you want the operating system to give you access to more cores, you have to tell the operating system that you have more threads, right? The other thing that happens is that the interleaving between threads that's visible to the threading library is invisible to the processor, or sorry, to the operating system. So, for example, in certain cases, you might want the operating system to know you have multiple threads because the operating system might give you more scheduling resources, right? It might say, hey, there's nothing running right now, I'll give you a couple more cores, right, or something like that. The final thing that's important here, and this is one of the things that makes user space libraries challenging, right, is again, the operating system only thinks you've got one thread. And so if that thread does any sort of blocking operation, if it tries to read from a file, if it uses the network, the whole process will block. You may have 10 other threads that have work that they could do. It doesn't matter, right? And so usage of these types of user space threading libraries is frequently sort of bound up in usage of various types of asynchronous I/O mechanisms that operating systems support, right? Because the goal is I do not want to block the entire process if any of the threads that are available have work to do, right? All right, so the pros, these are sort of just the inverse, right? The scheduling might improve because I can schedule all threads in the process and give them all access to resources on the system. The biggest con is the potential overhead of doing context switches between threads in the process, right? All right, so I think we will come back to this. This will be brief. We'll get through this on Monday. And then next week, we will talk about synchronization. So have a great weekend, guys, and get started on your homework.